Okay, the last lecture, the last lesson, we talked about chemical bonding, and we began by talking about ionic bonding. We said there are two main types of bonding that we deal with. One is ionic bonding, and the other is covalent bonding. Tribute to Johnny Cash. In this lesson, we're going to talk about covalent bonding. Now, covalent bonding is a type of bonding in which the two atoms that are going to bond together have a similar affinity for electrons. They usually also have a similar size. And they decide to share electrons between them rather than having an electron transferred from one species to the other, as happens in ionic bonding. Okay, if you remember the case with sodium and chlorine, sodium essentially loses an electron, chlorine gains an electron, so that sodium is positively charged, a cation, chlorine becomes chloride, a negatively charged anion, and then electrostatic attraction between the two holds them together. Well, in covalent bonding, the atoms that are going to bond have similar affinity for electron, and so one can't really win a tug of war for the electrons with the other, and so they decide to share. And the elements in the upper right-hand corner of the periodic table play covalent chemistry very well. That is, they form bonds primarily by sharing with other atoms, especially carbon, hydrogen, nitrogen, oxygen pretty much forms covalent bonds, and then the others listed here tend to be elements that form covalent bonds. To give you an example of what we're talking about, I have shown a reaction between two hydrogen atoms to form a bond, to ultimately form what we call H2, or hydrogen bonded to hydrogen. And I've represented the electron in the first hydrogen as a 0, and then for the second hydrogen as an X. This is just like tic-tac-toe. I have to I'm giving different symbols for the electrons so that you can tell them apart. So each hydrogen atom initially has a single electron. Now, if you remember the octet rule, or the version of the octet rule that says for the first row, if you have 2 electrons, then that's good. Well, if the 2 hydrogen atoms can come together so that each one provides 1 electron that then shares the space between the 2 hydrogen atoms, then each individual hydrogen atom actually thinks that it has 2 electrons, or that it has satisfied this special rule of having a pair of electrons. This is what we call a covalent bond, and we can represent that just because it takes time to draw out the X's and the O's and all of that. We usually just represent that with a dash in between the 2 atoms. The second example is 2 chlorine atoms. The first chlorine I've represented to have 7 electrons. Remember, chlorine has 17 electrons, but 7 in its outer shell. Instead of having 8, it only has 7 in its outer shell. Then I've also shown a second chlorine with X's for the electrons, showing that it has 7 electrons in its outer shell. So individually, the chlorine atoms have not satisfied this octet rule. They don't have 8 in the outer shell. But if they come together so that they share 2 electrons in the area between them, then each chlorine atom thinks that it now has 8 electrons in its outer shell, satisfying the octet rule. I've shown on the right a way that we can represent that with a dash instead of drawing out all of drawing the electrons in between, because that gets complicated. And the other X's and O's I just drew so that you realize that they are still there, but in many cases we ignore drawing those additional electrons, what we call non-bonded electrons, and would draw then the bottom drawing as the simplest way to represent the bond formed between 2 chlorine atoms. So remember, the take-home lesson is that if there's a dash between 2 atoms, that represents that there's a covalent bond with 2 electrons being shared in that bond. Now here are some other examples of molecules that are bonded together through covalent bonds. Now one of the first things you'll notice is that they can have more than one bond. So two oxygen atoms, for example, can form a double bond. That is, two situations in which they share a pair of electrons between the oxygen atoms. Now, as you might guess, a double bond is stronger than a single bond. So oxygen forms a double bond. Nitrogen, two nitrogens come together and they share three pairs of electrons. They have a triple bond. That makes diatomic nitrogen, the nitrogen that is in our atmosphere, a very stable molecule. The next molecule I've drawn is ammonia, just like the ammonia you have in many cleansers. It has nitrogen in the middle. That nitrogen is bonded to three different hydrogen atoms. And the last one I show here is carbon dioxide. In carbon dioxide, the carbon is in the middle, and it's bonded to two oxygens on each end with a double bond between the carbon and each oxygen. Now, anytime you have double bonds, they tend to be more stable than single bonds, and so as you might imagine, carbon dioxide is a very stable molecule. Now, the sharing of electrons, remember a dash is a shared pair of electrons. The sharing of electrons between two atoms is not always fair or always equal. For example, if we consider water, H2O, oxygen, and then it's bonded to two different hydrogens, okay, with a covalent bond between the central oxygen and each of those hydrogens. But oxygen is essentially an electron hog. That is, it just wants everyone else's electrons. It has what we call a high electronegativity. It likes electrons. Okay, the consequence is that it will not share the pair of electrons equally with hydrogen. Hydrogen is kind of small and wimpy. So this is what we call a polar covalent bond, where most of the electrons of that pair, of that bonded pair, actually spend their time around the oxygen rather than around the hydrogen. But the hydrogen, it just doesn't know what else to do. It says, well, at least I think I have two electrons. So we have polar covalent bonds, and the result of this is that the hydrogen atom will be partially deficient of negative charge. It won't see as much of the pair of electrons as does the oxygen, and the oxygen atom will see an excess of negative charge. And as shown to the right is a way we can depict this. We can draw water with the oxygen, the central oxygen, being partially, a little delta means partially negative, and the two hydrogens being partially positive. Now, a consequence of this is that water molecule actually has something of a partially charged nature, a separated partially charged nature. The oxygen being partially negative and the hydrogens being partially positive. Now, if you remember with ionic bonding with sodium chloride, the attraction was really between opposite charges, the sodium and the chloride. Well, if two water molecules can come next to each other, a partially positive end of one water molecule can interact through an electrostatic interaction with a partially negative end of the other water molecule. Okay, that is, there can be weak coulombic or electrostatic attraction between water molecules. A consequence of this is that water tends to be more stable in its liquid state and in its solid state than other molecules of its size, meaning that water has a relatively high boiling point and freezing point, or melting point. MP is for melting point, for its size, because it forms these hydrogen bonds between individual water molecules. Or in other words, water is a very stable condensed phase of matter for a molecule of its size. Now, these hydrogen bonds, which is what we call this weak interaction, which I've represented with dashed lines, a hydrogen bond is important not only in stabilizing water, making water be stable in its condensed phase, but also can form between water and other molecules, and between other molecules that also have this this ability to form polar covalent bonds. Now we see this a lot in biological molecules, and later we will talk about hydrogen bonding being important to stabilize the structure of proteins and to stabilize the structure of DNA. You may recall, if you've had a course in biology where we've talked about the hydrogen bonds between the A and T and the G and the C base pairs in DNA. This is the basis for those type of interactions. Now, a hydrogen bond is much weaker than a covalent bond. The covalent bonds, which we draw as a dashed line, are stronger, and the dotted lines for a hydrogen bond may be 5 to 10% as strong as the solid lines for a covalent bond. This also gives rise to the phenomena of acidity in water and helps explain some of the solubility properties of water. That is, as you may know, water will dissolve a number of compounds such as salt, but it will not interact with other molecules such as gasoline or oil. That's why we say oil and water don't mix, but water will dissolve salt and sugar and other things quite nicely. The reason that water dissolves salt is because of this electrostatic interaction between the partially positive and partially negative ends of water molecules and the cations and anions of sodium chloride. So polar covalent bonds turn out to be fairly important. Now, let's continue to talk about water and how we can represent water. H2O is what we usually tell people when they ask us what is the chemical formula for water, H2O. But we like to draw out the structures of molecules when possible so that we can understand them better. Now, one thing to realize is that H2O, while you probably would guess that oxygen is in the middle, it's not a linear molecule. It's not as drawn in the first representation. Actually, it is a bent molecule. And at the upper right-hand corner, I draw the structure of water with the individual oxygen-hydrogen bond angles drawn out. They're about 105 degrees, whereas if it were to be a linear molecule, that bond angle would be 180 degrees. Okay, so water is a bent molecule. Now back over to the left, I show what is called a stick drawing, which attempts to illustrate the size of the individual atoms a little bit better. And oxygen is oftentimes drawn in red just because we have to have a color scheme to use. And hydrogens are usually drawn in white. And so the first red and white structure is what we call a ball and stick representation. And the one below it is called a space-filling representation. You can see different ways that we can represent water. To the right, at the top, we first show again the bond angles and the bond length. The bond length, 95.84 picometers. Now, picometer is 10 to the minus 12th meters, and it's a very, very, very small number, but in fact, we do know something about the dimensions of the bond between oxygen and hydrogen in water. It's very small, but it is known, 95 picometers. The next representation again shows the charge separation in water, where the oxygen is partially negative and the hydrogens are partially positive. And then at the bottom right, I show you drawing to illustrate hydrogen bonds, showing that an individual water molecule can actually form a hydrogen bond with 4 other water molecules, thus forming the hydrogen bonding network in both liquids and even to a greater extent in the crystal form of water. We're going to pause again and I'll ask you a few questions, then we'll come back to lesson 3 on chemical bonding and chemical reactions.
I keep my eyes wide open all the time. I keep the ends out for the tie that binds. Because you're mine, I won't